Thank you. Yes, the 100-year web. Let me just first, though, talk about who I am and why I'm here. And why am I... Yes. So, some of my background, I went to the same school as Stephen Hawking. I didn't actually know him, but he was a few years ahead of me. But the boy behind me at school is now the Stephen Hawking professor of physics in Austin, Texas. So I still have some sort of contact with him. But somebody I did know was my university tutor. He was Richard Grimsdale. He built the first ever transistorized computer. And the interesting thing about him is that he was a tutee. I'm going to stand over here. Yeah, he was a tutee of Alan Turing, which makes me a grand tutee of Alan Turing. So after university, and entirely coincidentally, nothing to do with my tutor, I went and worked in the department where Alan Turing used to work, and I worked on the 5th computer in the series of computers that he worked on. He worked on 1, 2, and 3 before he died. In fact, last month was the 70th anniversary of his unfortunate death. So yes, I worked on the 5th computer in the line of computers that Turing himself had worked on. So after that, I did some things, and then I ended up in Amsterdam, where I've spent actually most of my life, and I co-designed the programming language that Python is based on. So that's Guido van Rossum in the middle there. This was one of our project meetings. That's me, if you can't recognize me there. As it happens, I was the first user of the internet in Europe, November 1988, so just over 35 years ago, when the CWI, where I work, set up the first European internet node, open internet node, and then they created 2 spin-offs to build the internet out in Europe and the Netherlands. Which meant that I ended up getting involved with the web right from the beginning. I organized workshops at the first web conference at CERN in 1994. This is me singing a song with Tim Berners-Lee, the inventor of the web there. And I ended up working at W3C, where I co-designed HTML, CSS, XHTML, XForms, RDFA, and a number of other technologies. And I'm still chairing 2 groups there, XForms and IXML. Now I'm going on to my talk, but I want to give you a trigger warning that I may well say things that you'd rather not hear, and I apologize for that. It's not the first time that I will have done such a thing at a conference. In 2008, for instance, I gave a talk to a Web 2.0 conference where I gave a talk about the dangers of Web 2.0. And the audience were furious with me, and they were furious with me basically because I was right and they didn't have any answers. A few years later, I got this comment: the crowd completely disagreed. In hindsight, he could not have been more correct. It grows more relevant with each passing year. So one of the advantages of all this, being here in a big group like this is that you can form a support group at the end of the day. So, now the talk. So, New College, Oxford, 1379, that's when it was built and opened. It's called New because it's 1378. Most of the other colleges had already been built. And it's sort of got a Harry Potter-like dining hall inside with huge oak beams right at the roof. Now, eventually, and we're talking about 100 years ago or so, the beams needed replacing. And the problem is that oak beams are really hard to locate. So they realized that the university had a forester, so they thought, well, let's ask him. Maybe he knows where we can get oak beams. So they asked him, and he said, which college are you from? And they said, New College. He said, well, I've got your trees. And what turns out is that about the time that they built New College, they planted new oak trees to be ready for when they would need replacing. So that's quite amazing sort of thinking that nowadays we don't hear much of, and that's the sort of thing that I'm going to be pointing out in this talk. So 2024, this year is the 33rd anniversary of the web being announced in 1991. It's, as I already said, 35 years last November since the internet started in Europe. But on that day in 1988, in fact, public computing was only 31 years old. This is a picture of the very first municipal computer ever installed in the world, as it happens, weirdly, in Norwich, UK. This is only one of 21 boxes that they had to unpack for that computer. But my point is that computing is actually very young, that when the internet started, public computing was only as old as the internet is for us now. Thank you. Did I jump one? No, I didn't. Okay, so 1991, the web was announced, and many people think that Tim Berners-Lee must have been a genius to have invented such a thing. But in fact, at that time, there were several competing variants of the web being developed. So the original web wasn't really revolutionary. It just created the right combination of a number of existing elements. It was simple. It integrated existing information services that already existed, like FTP, so it meant that you could build your website really, really fast. And the most important one, maybe, is that it was free, because all the competitors you had to license, and it actually cost you money. So I think that's what gave him the benefit. And the last thing that I think really made it important, and I want to talk a lot about, is that it was declarative. So let me just point out what declarative is and why it's advantageous. So at school, we learn about numbers, about addition, multiplication, division, and so on. But at a given moment at school, we learn our first declarative definition, and that is for the square root. A square root of a number is a number that when you multiply it by itself, you get the original number back. Now, this is declarative. It tells you what a square root is. It tells you how to recognize it, but it doesn't tell you how to calculate it. So most people know what a square root is, but very few people actually know how to calculate one except by pressing that button on a calculator. So here's the procedural definition of square root. And in fact, I would claim that if I hadn't told you that this was for square root, that you would have a great problem in recognizing what this bit of code for. When you look at this, it looks complicated. What does it do? Under what conditions does it do it? How does it do it? What's the theory behind it? I know the theory behind it, and actually it's quite hard to see because certain things have been optimized so that it's difficult to pull the theory out. Is it correct? Can I prove it? Under what conditions may I replace it or part of it with something else? So as you can see, a declarative definition is much shorter. It's much easier to understand. It's independent of the implementation. It's less likely to contain errors because it's shorter. It's easier to see that it is correct, and it's tractable. Now, what do I mean by tractable? I'll come to that in a minute. So HTML, when the web came out, was more or less a declarative language. That is to say, so I'll talk about that in a minute. Now, in the early days of HTML, there were very few browsers, of course, and only one or two of importance. The browser manufacturers were in a particularly position of power because they were implementing HTML, so they were in the position of being able to add stuff to it. And they didn't understand this declarative basis of HTML, and so they made a number of stupid mistakes, some of which we still have to live with today because of the bad design decisions made by Netscape. W3C was partly created in order to protect HTML and to get it back so that everybody was using the same HTML and not that each browser was doing something different, and that everyone agreed on new features and weren't just added willy-nilly. Unfortunately, recently, browser manufacturers, led by Google, have taken over the design of HTML, and they're changing it radically, and actually they're making a terrible mess of it. And I will talk about some of that mess now. But they're largely forgetting the declarative foundation of HTML. So let me just talk about how they define HTML. So this is how I would declare numbers declaratively. I would say a number consists of an optional sign and then a number of digits, digit plus meaning one or more digits. And an optional sign is a minus sign or that's optional. And a digit is any character in 0 to 9. And I can just say a number has its normal everyday meaning. Now, this is short, it's easy to read and interpret, it uses a standard, widely used notation, and it's tractable. That is to say, I could feed this into a program that generated a parser to do the right thing, that recognized numbers. Now, this is the text from the HTML5 specification that actually specifies exactly the same thing. So this is page 1. This is page 2. The bit in bold is where they've made a mistake. There's an error. This is page 3. Yeah, so the HTML5 definition of numbers is 16 times longer, and it's got bugs in it. So it won't surprise you to know that the HTML5 specification is very large indeed. Now, this was 2009. It's surely got bigger since then, but I'm not going to print it out just so that I can make a picture of it. But it's thousands of pages of difficult-to-read text, like as I just showed you, in a procedural style. And that's because the people designing it are basically programmers who've designed the specification as if it were one big program. So declarative methods are not just for specifications, but also for notations. So for instance, HTML, an element like H1 just announces that it's the top level heading. It doesn't require anything about it, about the font, or that it's large or it's bold. In fact, it doesn't even say that it is actually a font. It could be just as well read by a voice browser. Or the A element contains an enormous amount of information in a very small space. It encapsulates what it looks like, what to do when you hover over the link, what happens when you activate it, what are the methods of activating it, what to do with the result, and giving you hooks for presentation changes. So it's almost the poster child of declarative markup. CSS, the web styling language that this markup then allows, is another example of a successful declarative approach. And I'm glad to see that somebody's giving a talk this afternoon on how to use CSS instead of JavaScript to achieve lots of effects that people are using JavaScript for. When W3 started the CSS activity, which I was a member of, Netscape at the time, which was at the time the leading browser, refused to join, or declined to join at least, saying that they had a better solution called JSSS, based on JavaScript. So that instead of writing it declaratively, you wrote it as a part of a program. So that brings us to JavaScript, which is the basis of many, many websites now. JavaScript, a language that's so good, it has good parts. And when people ask me how should they learn JavaScript, I always say, go to this book and no other, because the good parts are. So, you know, I don't need to say anything more about that. But what I do want to say is something about the consequences of turning the web into a programming environment. Because beforehand, it was declarative. You said what you wanted, and you let the browser do the stuff. Nowadays, you program what you wanted. So you say how to do it without saying what you want to do. So I want to talk about some of the consequences of dropping the declarative approach for programming. One of the things is standardization. So standardization disappears, and this, what I'm using now, is a very good example of that. This is CSS presentation mode that I'm using. My slides are in HTML, and they're being displayed here using a special part of CSS, which says how to display them when you're displaying it on a screen. Unfortunately, HTML5 took the approach that it would be far better to do this in JavaScript, so they dropped CSS presentation mode. I've no idea why. I think it's a stupid mistake, but there you go. So no one supports presentation mode anymore, and in consequence, there are really lots and lots of presentation packages written in JavaScript to do presentation. But the problem is they're all different. I can no longer switch to a different presentation package and use that, because I have to change all my documents. They all depend on being written in a different way, specific for that package. So what this means is that programs are doing document design, so all the documents essentially are becoming proprietary. And so there's no interoperability. You can't move your document from one place to another. You're stuck, you're locked into one package. Another consequence is divergence. JavaScript is there, is being used, so that's why there are so few new elements in HTML5 compared with its predecessor. They haven't done any design and instead said, if you need anything, design it yourself and do it in JavaScript. And that's what has happened. And so now Wikipedia lists 26 packages of JavaScript, like Angular, Dojo, Bootstrap, and so on, that you can use to build your web pages. But the problem is they're not interchangeable, just like the presentation mode. Thus, we've effectively created 26 different versions of HTML. Now, what happens if your package... So first you have to decide which framework you're going to use to achieve these effects. And what happens when your program, your package dies, the people supporting it no longer support it, or it doesn't get updated for all the versions of all the browsers, or the owners change the license terms, which has happened fairly recently. You have to then reprogram your whole website. You have to change everything, which is exactly why we have standards, so that you don't have to do that sort of thing, so that you can move your website from one place to another without having to rewrite anything. There's another consequence, and that's availability. The UK's government digital service ran an experiment to see how many of its users did not receive JavaScript-based enhancements, and discovered that 1.1%, or 1 in every 93 users, didn't get those enhancements. Now, for Amazon, for instance, that's nearly 2 million people a month, which is a very large number. And then you get bloat. So if I want to look at the web page of one single tweet, which is 140 characters long, right? I have to download just under a megabyte, 5,200 lines of HTML and the 5 JavaScript packages. Now, I should point out that James Joyce's Ulysses is only half as long again. So this is an enormous amount of text that you have to download just to look at 140 characters. And I love this quote about the website Obesity Crisis. An article from 2012 titled "The Growing Epidemic of Page Bloat" warns that the average web page is over a megabyte in size. The article itself is 1.8 megabytes. 2 years later, an article called "The Overweight Web" warns that average page size is approaching 2 megabytes. The article itself is 3 megabytes long. So, and this was written a few years ago, if present trends continue, there will be a real chance that articles warning about page bloat could exceed 5 megabytes by 2020. Speed as well gets affected. This was very nice because of the European privacy law, GDPR. USA Today decides to make a European version of their website for EU users, which is kind of worrying as well, because that means that their site really isn't very good at privacy. So what they did was remove all the tracking scripts and ads. And this person who's writing here did a comparison of the two. The page went down from 5 megabytes down to 500 kilobytes. A load time of more than 45 seconds was reduced to 3 seconds. And of course, 124 JavaScript files to 0. So add the total number of requests from 500 down to 34. So in other words, adding all this bloat has a consequence of making websites much slower as well. And finally, accessibility. One day, all of you will be 80 years old. And all of you will, or most of you, will have bad eyesight. But of course, the web is a fundamental part of society, so you will absolutely need, not just want, but need to be able to access the web. And so you will need accessible websites to make it easier for you to read what's there. And we're losing that ability because of moving to programming. And this quote here, many developers who have grown up only using frameworks have a total lack of understanding about the fundamentals of HTML, such as valid and semantic markup, which is the basis, the core principles of an accessible web. Oh no, and one more, permanence. So the web is now the way that we distribute information. A lot of books are disappearing. Train timetables, dictionaries, encyclopedias, many things are now migrating to the web and disappearing as paper. The problem is that this is all part of the basis of our society and a part of our basis of our future history, as it were. And we should be able to read this information in 100 years' time, just as we can now read 100-year-old books. But I see a problem in the future of people depending on a particular 100-year-old implementation of JavaScript or framework to be able to look at the information again. And I think this is not an evidence of future thinking. The nice thing about declarative markup, it's easier to keep alive because it's independent of implementation. So let's go back to 1957 again, and that first municipal computer. So in 2015, this is the same building, by the way. In 2015, so let me just go back. This is the same building. 2015, the Raspberry Pi Zero was released, which was a milestone computer because it was the first computer that was so cheap it was given away for free on the cover of a magazine. So. So the Elliot, that's 1957 computer, ran for about a decade, 24 hours a day. So I just want you to think for yourself, how long do you think it would take the Raspberry Pi to run to duplicate that amount of computing? And these are all basically in steps of 10. Do you think it's about the same, 10 years, or do you think it's 10 times faster, or how long? You know, just think for yourself. Well, the answer is 5 minutes, because the Raspberry Pi is 1,000,000 times faster than that initial computer that was installed in Norwich. But the Raspberry Pi is not only 1,000,000 times faster, it's 1,000,000th of the price, roughly speaking. So it's a factor of 1,000,000 better, which is a tera. So a terabyte is 1,000,000 bytes. So we talk in very large numbers these days. For instance, 1,000,000 seconds is 30,000 years. So the number of bytes on a disk nowadays is absolutely enormous. And because we just say terabyte, we don't really grasp how enormous those numbers are. In fact, 1,000,000 times improvement is about what you would expect from Moore's law over 58 years, except that the Raspberry Pi is 2,000,000 times smaller as well. So it's actually much, much better even than that. Now, in the 50s, computers were so expensive that almost nobody bought them. In fact, you almost always leased them. And as part of the leasing, you would get a programmer or one or more programmers as a sort of sweetener, because they would know how to program it, and they'd be able to teach other people. And similarly, to rent a time on a computer in those days, it would cost $1,000 per hour in 1957 already, which was more than the annual salary of a programmer. So what this means is that compared to the cost of a computer, a programmer was almost free. So this economic relationship between computer and programmer was the basis of the original programming languages that were designed around that time in the mid-50s, COBOL, Fortran, Lisp, and Algol. They were designed with that idea that the programmer is cheap and the computer is expensive. So they were designed to save computer time and not to save programmer time. It was much cheaper to let the programmer do loads of work than let the computer do some of the work. So programming languages were designed so to tell the computer exactly what to do in its terms and not in the terms of the programmer, what you want it to achieve, what you want. So now, if we go back to now, it happened very slowly, gradually, almost unnoticed, but nowadays we have exactly the opposite position. Compared to the cost of a programmer, a computer is almost free. It's a trivial cost in relationship to the cost of a program. So I call this Moore's switch, and here is a sort of graph that's showing the change, the plummeting in costs of computers in those years, and the gradual but inexorable rise of the price of a programmer, and that's a logarithmic scale, by the way. So it's a huge difference. In 1957, a programmer got about $300 per year as salary. But the funny thing is that we're still programming in languages that are visibly descendants of those programming languages that were designed in the 50s. We're still telling the computers what to do. It's as if we're still thinking that the computers are expensive. So I want to talk briefly about declarative programming, which is a new way of programming. It describes what you want to achieve, but not how to achieve it, and it leaves some of that work, at least, to the computer. So let me just give you a very small example of declarative programming. So if you want to create an analog clock on your screen in standard programming languages, well, I went looking for C programs that did that. This is the smallest I could find. It's 1,000 lines. The largest was 4,000 lines. But in fact, only 2 or 3 lines have anything to do with time at all. All the rest is more or less administrative stuff. So now let me show you the code in a declarative system. So you say a clock has just got 3 fields, hour, minute, second, which do display, so this is a sort of style sheet, you display as a circle around a combination of the hand, the minute hand, the second hand, and some decoration. And a second hand is a line of some length rotated by the number of seconds times 6, because seconds go from 0 to 60, so that's going from 0 to 360. And then you declare a clock and you say, well, the seconds field, and this is an equality, it's not an assignment, it says it's always true, it's a bit like in a spreadsheet, so that if one of these changes, the other changes all the time. So you just say that the seconds field is the system seconds modulo 60, and so on. So this is a screen dump from 1993 that I made of just that code working. Well, the code was slightly different. But every second this would tick. This is running on an Atari ST, so it doesn't demand a lot of computing power. And every time the seconds changed, the system seconds changed, then all the other things here changed to match. And here's the modern version using a different programming language. So this is just the code that I just showed you, and it's just a handful of lines of code. So we've been working, as you see, on declarative languages for more than 30 years. 1993 was when it was already working. But as a result, we've experienced now of people building large systems using declarative languages, and I want to tell you just about 3 of them. So the first one is a company, I can't tell you who they are, because I've got a they only told me this as long as I didn't say who it was. But they make enormous machines, and I like to say, well, imagine it's a ship. You build ships one-off, the customer says they want a ship, you build it. The user interface of a ship is enormous, of course, very complicated, and it's all got to be in that one control room at the top. So they knew that building their ship would take the user interface, programming the interface would take 5 years with 30 people. And then one year they decided to use a declarative language to try it out, and they did it in 1 year with 10 people. So if a programmer costs 100,000 a year, then they've gone from a 15 million cost to a 1 million cost, and they've saved 14 million and 4 years. The next example is in insurance, in a British insurance company. The manager had heard about declarative programming and so said to the person who knew about declarative programming and to the regular programming manager, here's the next application we want. I want you to go away and come back in 2 days and tell me what resources you think you're going to need in order to program this application. So 2 days later, the programming manager came back and said, 2 days wasn't enough. I need 30 days to work out how long it's going to take us to program it. And the declarative programmer said, I've already programmed it. It's running now. My last example, and the most recent and actual one, is the National Health Service. The British National Health Service started a project a few years ago for a national distributed health record system. They put an enormous amount of money in, £10 million at least. The slides will be online. You can follow those links to read about it. It involves 70 programmers. The hardware costs alone were £5 per patient, and we're talking about 60 million patients here, so that was really, really expensive, and basically it failed. It did run, but really, really poorly. So one of those 70 programmers went away and programmed it using a declarative language instead. He wrote it single-handedly in 3 years. The hardware costs are 1 penny per patient. It even runs on Raspberry Pis if necessary, and it's now running in a number of British hospitals. And the great news that I recently heard is it's now being rolled out in Ukraine, which is the place where they really need a distributed system, because if one hospital gets blown up, at least you haven't lost all your data. So my conclusion is that the web is too important as infrastructure to be treated lightly. We mustn't just throw away our websites and our data when we think it's out of date. We've got to let it hang around, and we mustn't depend on programming. We should use declarative foundations so that the structures and the information remain for future use. But also it's a question of attitude, that when you're designing, design with the future in mind, not just the present. Thank you. Time for questions?
Yeah, so anyone has a question? We've got some time for a couple of those. No one?
Yes,
Yeah.
a hand. I'm going to walk up to you so I can hear you.
Oh, I can also...
Oh, yeah, all right.
Yeah, I was just wondering, like, how optimistic are you about any change as you see it? I mean, do you think we'll go forward with this approach, or are we going to continue with, you know, JavaScript and changing frameworks every 2 years?
Well, so my talk the other day on the business track, my conclusion was that the old generation has to die before these changes can happen. And so I could give the same answer now. But I believe that in 100 years' time, if we're still programming, that is to say, if the climate crisis hasn't killed us, that will be declarative programming, just because it's so much easier. I mean, you know, I can create an app in such a short time now compared with, and I mean, I still program in both procedural and declarative languages, but declarative is just so much easier. And I don't necessarily think that the programmers will fight for it, but once the managers hear about this, I don't think there's any way back.
Yeah.
First of all, thank you for a great talk. And my question is, in your opinion, what's the worst part of JavaScript? There's so many of them, right?
So what you do is you take that thin book and you subtract it from the big book, and that's the worst part.
No, you have to name one thing. You're not getting away so easily.
The design.
Very general, but thanks.